We are moving on to Part C. We're still on the June 2019 exam. This is the last part that goes in our answer booklet and the last part of the exam. Remembering we have to write this in pen, so let me just flip the page. Here we're ready for Part C. Okay, so let's get started. So I have some reading here for 66 through 69. But remember, a good strategy for this exam is skip this reading for now and go to the question. Write a chemical name for the compound that decomposed. Okay, well, if you can see, it says the unbalanced equation in the data for the decomposition of solid this. So this is what decomposed. So I need to write a formula for this. Okay, well, K, if you remember, is in Group 1. It is a metal. Okay. K, the name of K is potassium. So since this is a metal, that means this is an ionic compound. So that means since I have more than one thing over here, I have to look at table E, because the K is the positive ion. So this thing must be the negative ion, but I can't find the name on the periodic table or table S or anything. I got to go to table E, and I'm going to look for ClO3 right here, chlorate. So the name of this is just potassium chlorate. So potassium chlorate, right? Potassium chlorate. All right, next question. Based on the lab data, show a numerical setup to determine the number of moles of O2 produced. Use 32 grams per mole as the gram formula mass. So what I need to do is find the formula. If it says gram formula mass, I'm finding number of moles. I need the mole formula. So the number of moles is given mass over gram formula mass. So I'm going to write that. Moles equals mass over gram formula mass. Okay, so moles equals, they told me to use 32 for the gram formula mass. So somewhere in my data, I need the mass of O2. And look, it's right here. O2 mass 0.80. That's it. I don't have to do the calculation. I stop there. I do not have to put it in my calculator, because all it said was to show the correct numerical setup. All right. Now, next question. Based on the lab data, determine the mass of KCl produced in the reaction. See how it's a question mark right here? So how do I find it? Well, let's see. Here's the empty crucible and cover. There's the crucible cover with this, so that's 2.07 is this whole thing, right? The crucible cover and KCl after heating is this. How much is the KCl? Well, I have to go back to my empty crucible and cover. Okay, so I need to take 23.41, which is the crucible cover and KCl, minus the empty crucible and cover, 22.14. And then I have to subtract those. So if you think you might make a mistake, what should you do? Well, you should use the calculator, right? So 23.41 minus 22.14 equals 1.27. 1.27. And the last one for this section, balance the equation in your answer booklet using the smallest whole number coefficients. All right, so let's look at it. Okay, do we know where to start? Maybe, maybe not. So one place you could start, see O has 3 on this side and 2 on this side. That might be a starting point. The other thing is, here is my best suggestion. Take the most complicated looking formula and put a 2 in front of it. and see if it works out. So let's try it. Put a 2 in front of the most complicated looking formula. So that means I have 2 times 1, I have 2 Ks. How do I make this side have 2 Ks? Put a 2 here. So 2 times 1, I have 2 Ks. 2 times 1, I have 2 Ks. Perfect. 2 times 1, I have 2 Cls. 2 times 1, I have 2 Cls. Perfect. 2 times 3, I have 6 oxygen. Right here I only have 2 oxygen. Can I make that be 6? I sure can. Do you know how? Put a 3. So 2 times 3 is 6 oxygens, and 3 times 2 is 6 oxygens. Voila, that's it. It's balanced. Now, how do I check if it's the smallest whole number ratio? Can I divide all of these coefficients by a number? Usually 2, but not always. Can I divide them all by a number to reduce them? No, I cannot. I could only divide them by 1, which wouldn't change them. Right? So that's it. It's balanced. You're done. So we are ready to move on to the next section of questions in Part C. So you can see 70 and 71 both have short answers. Again, 70 through 73, reading, data table. Let's go to the questions. State the number of significant figures used to express the mass of hydrogen carbonate ions in the table above. Okay, so calcium, magnesium, sodium, sulfate, hydrogen carbonate. So let's look at the mass. How many significant figures is that? Well, there is a decimal point, so I start over here on the left side. That's a 0, so I skip it. I start counting with this 1, 1, 2, 3. So my answer is 3. Based on table F. Okay, I need table F. Write the formula of the ion in the bottled water table that would form the least soluble. So least soluble means in table F it would be insoluble. Even though it tells you in table F at the bottom that it's not really insoluble, it just means just very little solubility. But anyway, the least soluble compound when combined with sulfate. Okay, so let's go to table F. There we go. All right, so with sulfate, right? Sulfate is soluble, but it has exceptions, which means when sulfate is combined with Ag+, it is not soluble, it is insoluble. Remember, insoluble means compounds that have very low solubility, right? So least soluble. So sulfate could be with Ag+, Ca plus 2, Sr plus 2, Ba plus 2, or Pb plus 2, and it would no longer be soluble. It would break its rule and be insoluble. So which one of those is included? Oh, Ca plus 2. Do not just write Ca. This table doesn't say just Ca, does it? No. 2 plus. All right, 72. Show a numerical setup for calculating the parts per million of the Na plus ions in the 500 gram sample of the bottled water. So I need the formula for parts per million, right here, mass of solute over mass of solution times a million. So I'm going to write the formula first, okay? So ppm equals solute, but that's grams, over solution, grams, times a million. 1 with 6 zeros. So let's go back to the data. It says the 500 gram sample of the bottled water. Well, that is going to be the solution. So 500 grams. Now I don't have to put the grams, okay, because I just need the numbers. But now I need the Na plus ions, and that is up here, 0.0033. 0.0033 grams. And that's it. Done. That's the numerical setup. I do not have to continue. I'm finished. Compare the radius of an Mg2 plus ion to the radius of an Mg atom. Okay, so compare means they're either going to be equal, one is going to be greater, or one is going to be less. So there's like ding, 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 you should know that. So either the Mg ion radius is equal to the radius of an Mg atom, or the Mg2 plus ion has a greater radius than the Mg plus atom, or the Mg2 plus ion has a smaller radius than the Mg atom. I just have to be real specific when I'm stating my answer, right? So Mg atom has 2 valence electrons. It loses those 2 electrons. So an Mg atom loses 2 electrons, right, to become an Mg2 plus ion. If it loses electrons, it gets smaller, right? So that means the Mg2 plus ion must be smaller because it has lost the electrons. I don't have them anymore. So I just have to be real careful when I say this, because I cannot say that the Mg2 plus loses electrons. No, no, no. I can say the Mg2 plus has lost, okay? Or I can say, to make it less confusing, the Mg atom loses the electrons, okay? And when we write electrons, we cannot forget the negative sign, okay? So the Mg atom loses electrons to become Mg2 plus ion. The Mg atom is larger in radius than the Mg2 plus ion. I could have worded it the other way and said that the Mg2 plus ion was smaller, right? But if I'm going to talk about the electrons at all, which in reality I don't even have to talk about this. This is what you had to understand. This is really what you had to write, okay? But again, you have to be careful. You cannot in any way state that this loses electrons, because it didn't. This Mg atom is what loses the electrons, okay? Now we are ready to flip onto the next section. Okay, so here we go, 74 through 77. 74 through 77. Identify the element in ethyl ethanoate. Remember, I just skipped the reading because maybe I don't need it. That makes it an organic compound. Okay, do you know what element makes organic compounds? Come on, you should know this, hopefully. Carbon, right? Carbon makes organic compounds. It's usually carbon with hydrogen, but definition, it's carbon. Write the empirical formula for this compound. Well, the empirical formula is the formula in lowest term, so I need the molecular formula first, so I need to count. We put the elements in this order, CHO. So I'm going to go through and count. 1, 2, 3, 4 C's. 1, 2, 3, 4, 5, 6, 7, 8 O's. 8 H's. And how many O's? 1, 2. Okay, that is the molecular formula, but I want empirical formula, so I need to reduce it. Can I divide all of these subscripts by something? You bet I can. I can divide them all by 2. And that will give me my empirical formula. Okay, and so that is what I'm going to write in my answer booklet. C2H4O. Remember, we don't write ones, so 2 divided by 2 is 1, but we don't put it in the formula. Write the name of the class of organic compounds to which this compound belongs. So I'm going to circle anything that's not just a carbon bonded to a hydrogen, and I see this. So that is the functional group. That functional group gives it its properties. It also gives it its name. Okay, so I'm going to look in table R for that exact functional group. C double bonded to an O, and then also bonded to another O. And here we have it, right here. It is an ester. So that's a simple answer. Ester. Look, 76 is not a long answer either. Write the... Okay, now we're on 77. Sorry. Okay, so we did 76, now 77. Determine the number of electrons shared in the bond between a hydrogen atom and a carbon atom in the molecule. So, any of these, between a carbon and a hydrogen, how many electrons are shared? Well, it's one line, right? So that means it's 2 electrons. Remember, when we write electrons, we have to write this, or you can write out the whole word, or one pair of electrons. Okay, here it would be 2, 4. 4 electrons or 2 pairs, but they didn't ask us that one. So it's just 2 electrons. That was kind of an easy one, right? All right. We have 2 sections left. Well, 2 question sections, right? We have this section right here based on an electrochemical cell, 78 through 80. Now, what kind of cell? Well, it literally tells me it's a voltaic cell. All right, so let me try and figure out everything I can about this electrochemical cell before I even look at the questions. All right, so I have an Mg electrode and an Ag electrode. Since it is a voltaic cell, that means I have chemical energy going to electrical energy because this is spontaneous, right? So when I look at table J for these 2 metals, Mg and Ag, so I look at table J and I find Mg, and then way down here is Ag. Mg is higher, obviously, right? So it is more active. In terms of metals, they're better losers. So that means, do you remember this? Leo says Gur. Better losers are oxidized. And then remember an ox and red cat. Oxidation is at the anode. So the higher one is the anode in this case, and that has a negative charge. The lower one is the cathode. That has a positive charge. So that means this is oxidation, this is reduction. This loses electrons, this gains electrons, which means the mass of this goes down, the mass of this goes up, and the number of ions of Mg would go up, and the number of ions of Ag would go down. Because you see we have the ions in the solution. So in this case, we're losing the atoms and they're becoming ions. And on this side, we're losing the ions and they're becoming atoms. So the size of this piece gets smaller and smaller, and the size of this piece gets bigger. When we run out of this, then the battery stops working, because this is literally a battery. Okay. That's a lot. We have electrons flowing through the wire. The electrons flow through the wire from anode to cathode. Okay, so let's see. State the purpose of the salt bridge. Okay, so that's just remembering. What is the purpose of the salt bridge? The purpose of the salt bridge is to allow ions to flow back and forth to keep the cell neutral, right? That's the purpose of the salt bridge. Okay. Write a balanced equation for the half reaction that occurs at the magnesium electrode. Okay. So at the magnesium electrode, we have oxidation happening. Here is the whole big equation. So like, don't start from scratch. So what you're going to do is take out the magnesium part from here. Okay. So I have Mg to Mg2 plus. But it is not done yet. A half reaction has to have electrons put in. Remember, we're losing electrons, right? And if you remember when we had to draw a number line real quick, 0, -2, -1, right? Going this way is Leo losing electrons. Going this way is Gur gaining electrons. And this arrow points to the side of the equation where you need to put the electrons. So they go on this side. Or think about charge. What is the charge of this Mg? 0. What is the charge of this Mg? +2. Well, I can't have an imbalance of charge. It needs to be the same. So how many electrons are lost? I went from 0 to +2. So I add my 2 electrons. Remember, I have to write this negative sign in order for that to be an electron symbol. So now this is plus 2 and minus 2, which does equal 0. So now the charge is balanced on both sides. Okay, so I'm going to write this Mg yields Mg2 plus 2 electrons. Okay. Last question for this section. Explain in terms of electrical energy. So I have to use the words electrical energy. How electrolysis reactions differ from voltaic cell reactions. Okay. So it's basically reverse. Remember how I said a voltaic cell converts chemical energy into electrical energy? Well, electrolysis is the opposite. Okay, so electrolysis uses electrical energy and converts it to chemical energy. But a voltaic cell converts chemical energy to electrical energy. All right, there we go. All right, we're done with this one. We're on our last question set right here, 81 through 85. Here's my paragraph. Skip it for now. Determine the pH value of a solution that is 10 times less acidic than the HCl solution. Okay, so I'm going to make a little pH scale right here. Okay, 0, 7, 14. Here we have acid. Here we have base. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13. Okay. When we go this way, H plus increases and it gets more acidic. When we go this way, H plus decreases and we get less acidic or more basic. Also, OH negatives would be increasing, and here OH negatives would be decreasing going this way. Because remember, even at this pH, the lowest pH, we have a whole lot of H pluses, very few OHs. At 14, we have very few H pluses and lots of OH negatives. But that's just like some background. Let's look at the HCl solution. What is the pH? The pH is 2. So here is where I am right now. This is where the HCl solution is. Determine the pH value of a solution that is 10 times less acidic. If it is less acidic, it has less H pluses, right? And if it is 10 times less acidic, this since the scale is based on logarithms, each jump in a number is 10 times. So that means either I go from 2 to 1 or from 2 to 3. Okay? Well, if it's less acidic, that means I need to go this way. So it's 3. So my answer is just 3. All right. State the color of the indicator brom-cresol green if it is added to a sample of KOH. Well, let's look up here. KOH, it doesn't tell me the pH. So what do I know about KOH? Well, KOH is a base. Bases have a pH greater than 7. Indicator colors are in table M. So let's go here. Brom-cresol, right? Brom-cresol green. So look at brom-cresol green. If the pH is below 3.8, it is yellow. If the pH is above 5.4, it is blue. So it's blue. Okay. And 83. Complete the equation in your answer booklet by writing the chemical formula for each product. Okay, so let's look at the equation in the answer booklet. We have acid plus base. So acid plus base yields water plus salt. Well, you should know the formula for water, H2O, right? Now we need to know what's salt. Well, what happens is this H right here and this OH right here join together to make the water, because we can actually write the water as HOH if we want to. Okay, so what's left? K and Cl. See how K was first in the formula, so put it first. Cl was second in the formula, put it second. Let's just check charges and make sure I don't have to do anything else. K has a +1. Cl, since it's last in the formula, uses the first one, -1. Well, +1 and a -1 balance. Voila, done. All right, looks like I'm done, but I'm just going to have to turn the page. I have 2 last questions. Okay. 84 says, show a numerical setup for calculating the molarity of the KOH solution. So first step is to get your formula, right? So molarity, MAVA equals MBVB. So MAVA equals MBVB. All right. Remember, from this equation, if we just look at it real quick, it really doesn't, it's not acid. It says the molarity of H pluses and the molarity of OH negatives. So if I just look at my formulas, HCl, which has 1 H, that's easy. KOH has 1 OH, so that's easy. So thank goodness they didn't make it more complicated. So now, show a numerical setup. I got to plug in all the numbers I know. So let's see, a 7.5 milliliter sample of KOH is, okay, so that's the volume of the OH. So that is VB. And I'm trying to find the molarity of the KOH. So I know that I don't know MB, but the VB was 7.5 milliliters. If the KOH is exactly neutralized by 15.0 milliliters of 0.10 molar. So the molarity is 0.010 molar, and the volume is 15.0 milliliters. Make sure to show that decimal point. So then that's it. I'm done. I do not have to do a single other thing. When it says show a numerical setup, you choose the formula, plug in the numbers, and stop. That's it. Done. All right, last question. Ready? Explain in terms of aqueous ions. So that means my answer has to talk about aqueous ions. Why 15 milliliters of a 1.0 molar HCl aqueous solution is a better conductor of electricity than 15.0 milliliters of 0.10 molar HCl aqueous solution. Well, conductors of electricity are acids, bases, and salts. It's the same substance, same volume. So why is it better in terms of aqueous ions? When there are more ions, it is a better conductor. So that must mean the 1 molar solution has more aqueous ions. So the 1.0 molar solution is a better conductor because, it has more aqueous ions. That's it. I mentioned aqueous ions and I answered the questions. Why is it better? Because it has more aqueous ions. And there we go. That is it. That is the end of the exam. Remembering you wrote in pen on all of this answer booklet. I hope that helped.